Hello everyone, welcome to my class. Today I am going to cover double integrals over rectangular regions and general regions. First, let me recall different integrals of function of single variables from calculus 1. The different integrals of f from a to b is defined as a single integrals of fx dx from a to b, which represents an area under the curve of fx from a to b. Now, in a similar manner, we can define a double integral for function of two variables defined on a bounded region. So the double integral template is double integrals of fxy over d with respect to dA, where d is a two-dimensional bounded region. This dA is an area element, so dA equals to either dy dx or dx dy. So there are two possible order of integrations to evaluate the double integrals. So the double integrals we can evaluate either with respect to y first and then the x, or first with respect to x and then the y. In this dx dy order, the x variable is an inner variable, so corresponding integral is an inner integrals. dy, the y is an outer variable, so the corresponding integral is an outer integrals. So quick remark, if function is constant one function, then the double integrals of 1 over d is simply the area of d. The double integrals of fxy over d with respect to dA computes the volume of the solid that lies above the plane region d and under the graph of f. So we can call the double integral as a volume integrals. In the diagram here, the domain is down here, and then the surface or the graph of fxy is in the up here. So the solid is between these two surfaces, so whose volume is computed by the double integrals. If domain is nice rectangular region, then the first diagram, if D is any arbitrary shaped domain, then the diagram is second. Okay, so the questions at this time, so we can ask to ourselves how to compute the limits for x and y integrals in our double integrals, so that we can evaluate the double integrals. Okay, so the simplest case is if D happens to be a nice rectangular region given by AB cross CD, then the double integrals can be computed easily with either first with respect to y and then the x, or first with respect to x and then the y with corresponding limits. These two integrals are called iterated integrals. So in general, if D is an arbitrary plane regions, now I am talking in this second diagram, if D is an arbitrary plane region, then we do have two ways to describe the domain. Let me scroll down. This is better. So the first way is describing domain vertically simple or y simple, where we describe the domain bounded above and below by the continuous function of x, and then the left side and then the right side by the constant value. So D equals to set of xy, where y is bounded between two continuous function of x and x is bounded between two fixed value. Means our double integrals can be written as double integrals of f over d with respect to area element dA equals to double integrals of fxy, so with respect to dy first, and y is an inner integral whose bounds are function of x, and then with respect to dx, so x integral is an outer integrals. So always keep in mind the inner integrals limits can be of at most on outer variables. So in this case, the y bounds are function of x is an outer variable, and then the outer integrals must have a constant limit. Now let's go to the second way, the B. We can describe the domain as horizontally simple or x simple, where we describe our domain as set of xy, where x is bounded between two continuous function of y. So here on the left side is continuous function of y, right side of this domain is continuous function of y, and then above and below is bounded by the constant values, so y values are constant here, so y equals to c and y equals to d. Then in this descriptions, our double integrals can be written as double integrals of f over d with respect to area element dA equals to double integrals of f of xy, and the order of integration is dx dy, so x integral is an inner integrals whose limits can depend at most on outer variables, meaning y, so x equals to h on y to h to y, and then we integrate with respect to dy, so y integral is an outer integral whose limits must be constant. Hopefully these two descriptions of the domain as well as these two setup for our double integrals make sense to you all. Great. Now let's use these ideas to solve the double integrals or to evaluate the double integrals. This is better. Oh, this is better. So let's start example 1. Find the volume of the solid that lies under the paraboloid. Paraboloid is given by z equals to x squared plus y squared, and above the plane region D in xy plane bounded by the two curves y equals to 2x and y equals to x squared. So first let's discuss the domain of integrations and then find the limits and then use the double integrals template and evaluate. So just a quick note, these two curves y equals to 2x and y equals to x squared intersects at point at 0, 0 means origin and the point 2, 4. So for this particular problem, let me do two ways. That means describing the domain as vertically simple and horizontally simple. So in the case A, let's describe domain as vertically simple. So here's our given curve is y equals to 2x, which is this diagonal line, and y equals to x squared, which is this parabola. They intersect as 0, 0 and 2, 4. So let's describe this domain as vertically simple. So draw a vertical slice and look for the y bounds. So y bounds is given by bottom curve, which is y equals to x squared. So y equals to x squared is your lower bound for y, and for the upper bound for y is given by this top curve where we exit the domain. So top curve, so y equals 2x, so y equals 2x is your upper bound for y. And to find the x limits, look for on that domain, look for x equals to minimum value and x equals to maximum value. X is 0 to 2. So with this domain descriptions, what's the volume template? So volume template is double integrals of f of xy with respect to area element dA over domain D. And we describe as y simple, so our dA equals to dy dx. So in the next step, what is our functions here? Our function is the paraboloid z equals to x squared plus y squared. So let's replace fxy by x squared plus y squared. So that's better. So fxy equals to x squared plus y squared. Then dA is dy dx. So first write dy integrals as the inner integral. So y bounds are y equals to x squared to 2x, and x integrals which bounds are 0 to 2. I hope this setup makes sense to you all. And then the next step, write down the x integrals. Then first integrate with respect to y, because y is an inner integral. So keep in mind integration of y, so x becomes constant, so here x squared is constant. So the integration of x squared with respect to dy becomes x squared times y, plus y squared becomes y cubed over 3, and put y bounds, y equals to x squared to 2x times dx. Correct. Let's move on. In the next step, write down the x integral 0 to 2, then put y equals to upper bound 2x and minus y equals to lower bound x squared, and simplify. This gives you this x integrals. And in the next step, just like calculus one, let's integrate these x integrals just by using power rule. So here, so 2x cubed becomes 2/4 x to the power 4 plus 8/3 constant pull outside, x cubed becomes x to the power 4 over 4 and multiply 4 and 3, that 12. Minus, as it is, x to the power 4 becomes x to the power 5 over 5 minus 1/3 x to the power 6 becomes x to the power 7 over 7, and you multiply 7 and 3 gives you this 1 over 21. And put x bound x equals 0 to 2, and on this last expression put x equals to upper limit 2 and minus lower limit 0. Lower limit 0 gives you all 0, so just put x equals to upper limit 2 and simplify, which gives you the answer 216 over 35. Great. Now let's do the another method, means describing domain as horizontally simple. So here y equals to x square, this parabola, y equals to x, 2x is this diagonal line. Now this times we describe the domain of integration as horizontally simple. So take a horizontal slice and we enter those regions at the left curve, so find the x value there, and exit on the right curve, find the x value there. So let's start. X lower bounds are given by this diagonal line, so which is y equals to 2x, solve for x, which gives you x equals to y over 2, so y over 2 is your lower bounds for x. And on that slice you exit the region on right curve. The equation right curve is y equals to x square, so solve for x, x equals to radical y, so x equals to radical y is your upper bounds for x. Great. Then for the y bounds, look for y equals to minimum value and maximum value. Y equals to minimum value is 0, maximum value is 4. As we said earlier, the 2, 4 is this intersection point. So now we have a limits here. So then let's evaluate the volume. So the volume template is v equals to double integrals of f of xy and with respect to dA, and dA becomes this times dx dy. So next step, let me scroll down, equals to write down the double integrals of integrand function is x square plus y square, just like in the first case, and integrate with respect to dx first and then dy second. Put x integrals as inner integrals and x bounds are y over 2 to radical y, and then the y integral is an outer integral whose bounds are 0 to 4. You can maybe let me take one moment to talk about when you change the order of integrations, then your corresponding limits also changes for the integrations, but the integrand function does not change. Let me draw this line here. Please pay attention here. So here your integrand function is same, x square plus y square, x square plus y square. We change the order of integrations, here dy dx, here dx dy, and our limits of integration changes here. So for example, the x bounds are y half to radical y, x bounds are 0 to 2, and here y bounds are 0 to 4, here y bounds are x square to 2x. Great. So now let's continue. Now I'm in this line. So write down the y integrals, then the inner integral is with respect to dx. So let's integrate with respect to x. Keep in mind y square is constant for x integral. So x square becomes x cubed over 3 plus y square becomes y square x, and put x bounds x equals to y half to radical y times dy. Then the next step, write down the y integrals, then simplify these expressions by substituting x equals to upper limit radical y and lower limit y half. Then this gives you these expressions. Now we have our integrals in y, then just as before, like here. Let's integrate with respect to y. So then the first terms, 1/3 pull outside. Integration of y to the power 3/2 becomes y to the power 5/2 over 5/2, but dividing is same as multiplying by its reciprocal, so flip that 5/2 to 2/5, and the constant is now 2 over 5 times 3, 15, so 215 y to the power 5/2 plus y power 7/2 times 27. Now we flip the constant. Minus y4 over 96 minus y to the 4 over 8. Put y limits y equals 0 to 4. And the last expressions, put y equals to upper limit 4 and minus y equals to lower limit 0, and simplify. This gives you the same answer that we got before, which is 216 over 35. So no matter which way we evaluate the double integral, we'll get the same answer. But in some questions, one way is easier than the other one. Okay, let's move on. Now let's do example 2. Evaluate the double integrals of x times cosine y with respect to dA over the plane region D, where D is bounded by the curve y equals to 0, y equals to x squared, and x equals to 1. So let's discuss the domain first. So here the domain is y equals to 0, x-axis, y equals to x squared, this parabola, x equals to 1, this diagonal line. So this is our domain of integrations, and we wanna describe this domain as a y simple, so that I can replace dA by dy dx and draw the particular slice here. And to find the limit, the y lower bound is given by x-axis, y upper bound are given by y equals to x squared, this curve, and for the x equals to 0, x equals to 1. Great. So now let's start evaluating the given double integral. So the double integral is double integral of x times cosine y dA over d equals to double integrals of the integrand function is x times cosine y, and in this y simple description, dA becomes dy dx. So y integral is an inner integrals and x integral is an outer integrals. And to find those limits, let's look here. So y equals to entering value, y equals to exiting value. So y equals to entering value is given by x-axis, so which is 0. So y equals to 0. And exiting value is given by this parabola. So y equals to x squared is an upper bound for y. Similarly, to find the bounds for x equals to minimum to x equals to maximum, so 0 to 1. So x bounds are 0 to 1. I hope this setup of double integral makes sense to you all. Now, next, let's start evaluating the double integral. Write down the x integrals. First integrate with respect to y. X is constant, so x times cosine y becomes sine y, and put y limits y equals 0 to x squared times dx. Then this equals to, write down x integrals and put y equals to upper limit x squared, so x times sine x squared, minus, put y equals to 0, sine 0 is 0, everything is 0. So now we have only 0 to 1 x times sine x squared dx. And this x integral is a good candidate for u substitutions. So let's substitute u equals to x squared, take the derivatives, du equals to 2x times dx, and at the same time let's change the limit of integrations. So at x equals to 0, u equals to 0, x equals to 1, u equals to 1. Then let's rewrite this x integral in terms of u integrals. Haha, not me integral. So in u integrals, this sine of x squared becomes u, so sine u, and then x times dx becomes du over 2 here. and then u limits u equals 0 to 1, u equals 0 to 1. Great. Then let's integrate this u integrals, the constant 1/2 outside. Integration of sine u becomes minus cosine u, so this minus cosine u, and put u bounds u equals 0 to 1. Then put, there is a minus, so let's put lower limit first. So cosine 0 is 1, so this minus, and the minus formula gives you plus half, and then put upper limit u equals to 1, so minus 1/2 cosine 1. So your final answer is 1/2 minus 1/2 times cosine 1. Great. Let's move on. Let's do another example, example 3. Yeah. Example 3 says, find the volume of the solid bounded by the cylinder x square plus y square equals to 1, and the planes x equals to 0, y equals to z, and z equals to 0 in first quadrant. Great. So let me talk about first the volume setup. The volume setup is v equals to double integral of fxy over d, and then the double integral is with respect to dA. Now let's discuss the domain first, then it's easier for us to determine the limits of or the bounds of x and y. So let's get the domain. So the domain is the projection of this cylinder on xy plane and is a first quadrant. That means circle, and the first quarter means 1/4 circle in first quadrant, which is just this part, right? And then to find the limit for our double integrals, let's describe this domain of integrations as vertically simple. So draw the vertical slice and look for the entering value to exiting value for y bounds. So the lower bounds of y is given by x-axis, which is y equals to 0. So y equals to 0, and exiting value is given by this curve, which is x square plus y square equals to 1. Solve for y. So y equals to radical 1 minus x square, which is the upper bound for y. And to look for the x limits, the minimum value and maximum value for x is x equals 0 to x equals to 1. These are the bounds for x then. Great. Now let's bring those bounds and put it here. So let's continue. So volume v equals to double integrals. So the y integral is an inner integral, x integral is an outer integral. So put the corresponding bounds that we found here. And now the integrand function is fxy. Fxy is z, z is y, so put y here. And dA replaced by dy dx. Great. Then first integrate with respect to y. So write down the x integral. So x integrals from 0 to 1. Then integration of y with respect to dy becomes y square over 2, and put y limits. Y equals 0 to radical 1 minus x square times dx. Then equals to, pull the constant 1/2 outside and write down the x integrals, and then put y equals to upper limit radical 1 minus x square. So this square cancel the radical, so simply 1 minus x square, and when you put the y equals to 0 lower limit, it gives you 0. So we have only this x integral left. Then it's easily we can integrate. So 1/2 outside, so 1 becomes x square becomes x cubed over 3, put x equals 0 to 1. You can scroll down, and now put x equals to 1 upper limit. So this gives you 1 minus 1/3. So this gives you 2/3. 2 to cancel 1/3. So now we find the volume of this given solid, which is 1/3. Great. Now let's move on. Let's do different types of problem in example 4. This is better. Evaluate the double integrals by reversing the order of integration. So the given double integral is I equals to double integral of e to the x square dx dy. The inner integral is x integral whose bounds are x equals 3y to 3, and outer integral is y integral whose bounds are y equals 0 to 1. So if you pay attention on this integrand functions and the order of integrations, so here we need to find the integration e to the x square with respect to dx. This is impossible. Even alien cannot do this without changing the order of integrations. So if we change the order of integration, then this dx dy becomes dy dx. So the integration of e to the x square with respect to dy, the e to the x square will be constant, then we can easily integrate. Great. So the idea is first sketch the domain of integrations and then describe the domain. The given domain description is horizontally simple. Now we need to describe our domain in a new way, which is a vertically simple. Then we can change this order of integrations. Okay, great. So let's look for the domain. Our domain is x equals to 3y, this diagonal line, x equals 3, this vertical line, and then from the outer integrals, y equals to 0 is x-axis, y equals to 1 is this horizontal line. So this domain is this shaded region. Now let's describe the domain as vertically simple. Then in vertically simple, draw the vertical slice. Then we found the y bounds as entering value, which is given by x-axis, so y equals to 0, and exiting value is given by this diagonal line, which is x plus 3y. Solve for y equals to x over 3. X over 3, this is 3. X over 3, maybe, yeah, x over 3 here. Same as here. And in the next, to find the x limits, look for x equals to minimum value and maximum value, which is 0 and 3. So these are the x bounds. Great. Now we are ready to switch the order of integrations and evaluate the given double integrals. So let's move on. So the given integrals I equals to double integral of e to the x square. Now in the new order is dy dx. In the y integrals, inner integrals, put y bounds here, and outer integral is x integrals, x bounds here. Great. Then first integrate with respect to y, where e to the x square becomes constant. So in the next step, write down the x integrals, and then integral of e to the x square with respect to dy becomes e to the x square times y equals to 0 to x over 3. Great. Let me scroll down. Yep. That's better. I'm here. Then in the next step, write down the x integrals and then put y equals to upper limit minus y equals to lower limit. Y equals to lower limit gives you 0, so just put y equals to upper limit, which is x over 3rd times e to the x square dx. Now this x integral is again a good candidate for u substitution, so let's put u equals to x square. Then its derivative is du over 2x, du equals to 2x times dx. Then du over 2 equals to x dx. We can also change the limit of integration, so at x equals to 0, u equals to 0, x equals to 3, u equals to 9. Then let's rewrite this x integral in terms of u variables. So e to the x square becomes e to the u, x dx becomes du over 2, and there is one more 3, so du over 6, and the new limits are 0 to 9, 0 to 9. Then integral of EU is EU itself, 1/6 is constant there, and put U bounds. Then we got the final answer. Our double integral equals to 1/6 times e to the power 9 minus 1. Great. So that is a quick note. Simply swapping the integrals does not mean a change of order of integration in general. I think this information I already talked to before. So now let's do example 5. Evaluate the integrals, the double integrals, given by I equals to double integral of sine of y squared times dy dx. So the inner integral is y equals to x to 1, outer integral is x equals 0 to 1. So now here we are first integrating with respect to y for sine of y squared. So again, this question doesn't say by changing the order of integrations, but by looking the integrand functions and then the order of integrations, this suggests us we have to reverse the order of integrations, otherwise the integration of sine of y squared with respect to dy becomes hard or even impossible. Great. So first let's sketch the domain, then switch the order of integrations. So in this given order is dy dx, which means vertically simple domain. Now we have to describe as horizontally simple and switch this dy dx to dx dy. Awesome. So what is our domain? Let's see. Y equals to x is this diagonal line. Y equals to 1 is this horizontal line. X equals to 0 is y-axis. X equals to 1 is this vertical line. So our region of integration is this shaded region. Then for new limits of integrations, describe this domain as horizontally simple and look for the x bounds. X lower bound is given by this y-axis, so x 0, and upper bound of x is given by this diagonal line, x equals to y. And for the y bounds, look for y equals to minimum to maximum. So y equals to minimum is 0, y equals to maximum is 1. So now we have these new limits for our double integrals. Then let's rewrite our double integrals. I equals to, the integrand function doesn't change, so simply sine of y squared. And then order is dy dx becomes dx dy. And then this under this double integrals, our inner integral is x integrals corresponding to dx. And put x bounds 0 to y. And outer integral is corresponding to dy is y integrals, put y bounds y equals 0 to 1. I hope this setup makes sense to you all. Then this equals to, now let's start evaluating the double integrals. Write down the y integrals, then integrate sine y squared with respect to dx. So sine y squared is constant for x integral. So then integral of sine y squared with respect to dx becomes sine y squared times x, and put x equals to upper limit to y. So this expression here. So y times sine of y squared du. Let me scroll down. This is again a good candidate for u substitution. So put u equals to y squared. Then its derivative is du equals to 2y dy, and change the limit when y0 u0, when y1 u1. So u bounds are 0 to 1 again. Then let's rewrite our y integrals in u integrals. So sine of y squared becomes simply sine u, and y dy becomes from here du over 2, and u limits 0 to 1. Now let's integrate. So sine u, pull constant 1/2 outside, then integration of sine u becomes minus cosine u, and the u bounds u equals 0 to 1. And then there is a minus, so to take out this minus, first put lower limits of u. So cosine 0 is 1, so plus 1/2 means 1/2, this means times 1. And then minus, put u equals to upper limit. This minus is not from formula, this minus is itself here, okay? And cosine of 1. So now we found the value of our double integral as 1/2 times 1 minus cosine of 1. Great. So we finished these double integrals over general regions as well as over rectangular regions. Now in the next sections or in the next lecture, we will study double integrals over polar regions, which is described by function of r and theta. Great. Thank you.